Good morning. I'm Christopher Lebrad, and welcome to this news briefing of the 254th National Meeting and Exposition of the American Chemical Society in Washington, D.C. We're joined today by Drs. Paola DeAngelo and Elizabeth Hirst from the U.S. Army Natick Soldier Research, Development, and Engineering Center. They have been developing high-tech materials that could keep soldiers both warm and battle-ready in frigid conditions. Dr. DeAngelo, would you like to begin?
Sure. Thank you for coming. What the U.S. Army is doing right now is we're trying to upgrade the cold weather uniform that the soldiers have to wear. Right now, it consists of 7 layers, and as you can imagine, 7 layers is quite a lot for them to wear. It increases their weight. So we're trying to minimize the weight load for them by coming up with a coating that is going to go in the base layer of the fabric of the uniform. And it consists of a layer of silver nanowire networks that will retain body heat, as well as it can be electrically conductive. And then it's going to have a hydrogel layer that Liz will talk about later that will absorb any sweat that the soldier expresses. So the garment won't feel as wet as if it didn't have the gel. So if you can, next slide. So this work was inspired by Professor Kui's work from Stanford University. He basically developed this silver nanowire synthesis, and he coated it on fabric, and he found out that the fabric formed a continuous electrically conductive network. So inspired by his work, we are tweaking things a little bit to optimize this coating and couple it with the hydrogel layer. So I don't know if you can see the pictures from the slides, but when we coat the nanowires onto the fabric, the nanowires nicely wrapped around the fibers, and it bridges between the fibers, forming this continuous electric conductive network. We have found out that if we hook up a battery or a power source to this coated fabric, we can increase the temperature of the textile by up to 110 degrees Celsius, which is enormous, an enormous change. Obviously, the soldiers wouldn't need that kind of heat, but it's just to show you the potential of how much we can heat up the fabric with just 3 volts, which is basically like a watch battery. So I do have a couple swatch that I brought here today. So this is bare cotton. It hasn't been coated with anything, and as you can see, it is not electrically conductive. It doesn't turn the LED on or anything like that. But with a simple coating that doesn't really affect the mechanical characteristics of the fabric, you can power LEDs, and you can also heat up the textile. So along with this, we're trying to couple this swatch with a hydrogel that Dr. Hirst is developing that will take care of sweat. So just to alleviate or to better thermal and moisture management for the soldiers.
Next slide. So the hydrogel coating will address moisture management for the soldiers. So one of the problems is that their base layers, while polyester, are very good at wicking water away from the skin. If you're in extreme cold, the rate of evaporation out of the fabric to the air is very slow, and consequently it's freezing. So frequently where their pulse points are, they're experiencing icing of the garments, which is obviously very uncomfortable. So we're hoping to apply a hydrogel, which absorbs, numerous times its weight in water to these problem areas to help move water away from the skin and out of the garment. And there are some examples of people using hydrogels for extreme heat to help, maintain moisture. So there's actually firefighter jackets that have polyurethane hydrogel liners to help keep the firefighter cool. So we're just simply hoping to take that same technology and apply it to the different end of the temperature extreme.
And I guess it's worth mentioning that the hydrogel that Liz has started developing can absorb as much as 40 times its weight. So 1 gram of powder of hydrogel powder, it's able to absorb about 45 grams of water. So the potential, it's there. It's worth mentioning that like right now the research is in its basic stages, and we're now moving into a more obviously applied early research and development.
Excellent. Thank you very much for that briefing. Are there any questions from the audience here?
Yeah.
Hi, so it's Kath O'Driscoll from Chemistry and Industry magazine. I was really surprised when you said there were 7 layers. I mean, how will this technology help to actually reduce the weight of the garment? Because I would think if you added the silver, wouldn't that increase the weight?
Yeah, so the idea is that the silver nanowire layer would go in to the base layer. So the actual coating would have 2 jobs. One is like any body heat that the soldier loses will hit the nanowires and bounce back towards the wearer, trying to keep their body temperature. And at the same time, if extra heat is needed, then they can just like power it up with a battery or something like that to increase the temperature of that base layer. So if you imagine that you can increase the temperature by 10, 20 degrees, they're not gonna need 7 layers of of garments. They can probably like reduce the number of layers by quite a few. And it's worth mentioning that the soldiers are not required to wear the 7 layers. It's up to them how many layers they choose to wear, but the soldiers that are fairly new and just enlisted, they don't know any better. They're like freezing, so they go ahead and wrap as much as they can, and then they start walking, they go on missions, and there's really no time for them to undress. So we're hoping that this technology would help them by reducing the number of layers, reducing the number of weight. Maybe at some point, if this gets developed further, they can dial up how much heat they need to keep their bodies warm. So there's a lot of potential here.
And what about, because I suppose a battery isn't really an ideal power source.
Yeah.
So what alternatives are you looking at? Is there anything that's sort of more practical for the field use?
Yes, so right now the soldiers have to carry batteries to power the radios and all that stuff, and as you can imagine, that adds tremendous weight. So we're trying to establish a collaboration with a professor at UC San Diego that has developed a flexible, stretchable battery that can be incorporated within the textile, and it's basically weightless. So we're working to partner with him to develop basically a weightless battery that will power the nanowires for however long the soldier requires. If that doesn't work, we have also considered maybe flexible supercapacitors that are pretty light in weight compared to batteries. The problem with supercapacitors is that it's a quick burst of energy, so the heating wouldn't last that long. So it depends on the application that, yeah.
Hi, Ben Valsler from Chemistry World magazine. The silver nanowire principle looks very impressive, but is obviously a lot harder to control than if you were to stitch in traditional copper wiring. So does the material heat evenly, or do you end up with hot spots from where there's a greiter density of
Yeah, and that's a great question, and I've had that question several times in the last couple of days during the poster presentations. We have acquired a pretty high definition thermal camera that shows exactly where the textile is heating as soon as we introduce voltage, and it is pretty even. There's really no patchy spots. Then scanning electron microscopy imaging has shown that the coating is pretty even throughout the fabric, and Some fabrics favor the coating compared to others. Cotton, for example, tends to be a little patchier, so I think we have to work a little bit on optimizing that coating a little bit for cotton. But then again, cotton is not one of the preferred textiles for the U.S. Army just because it doesn't wick.
Do you have any idea how resilient it will be to use as well? Are these going to be things that we can keep using for years, or are we likely to develop shorts and break the nanowires after 5-10 uses?
No, so that's an interesting question. They are incredibly robust. They are only like 70 to 100 nanometers in width, and they're tenths of microns in length. And you can like fold the fabric. We have done a few laundering testing with detergent and everything. And the nanowire stay for some of the fabrics. Other fabrics, we might have to think about chemically treating the fabric before it's coated with the nanowires. So just to increase the attachment of the nanowires, but it's pretty robust.
And with the hydrogel, how does the performance or the behavior of the material change as it absorbs water? Do you see any difference to the sort of saturated hydrogel compared to the fresh one?
So we're still in sort of the preliminary basic research. We haven't gotten quite to the coating swatches with the hydrogel yet, and that's simply because there was no literature on if you freeze a hydrogel and then thaw it, does it still work? So we kind of had to go back and answer those questions. You know, the Army wants to make sure we're not wasting our time before we can start coating swatches. But there is a body of work from the European Union on coating polyester with hydrogels, and the textile properties aren't there's no disadvantage to having the hydrogel coating, like the vapor transport and all that's still the same. So we're optimistic that the coating's not going to impact the comfort and breathability of the garment all that much.
Excellent, thank you.
So,
Can you please state your name?
Kathy Kowalski, freelance. When you describe the hydrogel, it sounds a little bit like a super soaker chemical from a baby diaper.
Yeah.
Yeah.
And so I guess what my first question is, how do you get it on? And how do you get it to unsoak when you clean it? Because if you throw it in your washing machine, is it going to absorb more water?
Right.
So just practically, how do you get it to discharge so you can use it again?
So we're hoping to take advantage of the large body of literature on thermo-responsive hydrogels. So we envision actually coating the fabric with microgel particles. So it'll be tiny, tiny little particles. And then depending on which polymer you pick, there's a phase transition at a certain temperature where the gel goes from absorptive to non-absorptive. And so there's a couple different polymers we could pick from so that we could sort of dial in at what temperatures we want the particles absorbing and at what temperatures are they going to shed their water. So we could try tailoring it so that the particles absorb around what your skin temperature would be while you're sweating, and then anything lower than that, they shrink and the water gets shed. So the idea would be once you take the garment off, because these soldiers are out on missions, a couple days, they might switch base layers. While your base layer's in your backpack, it could be shedding the water, and that would give it enough time to evaporate out eventually while you're not wearing it.
Okay, and then you need like a little drainage system for it or something
Yeah.
like that, like wringing it out.
Or, if you picked a polymer that shed at higher temperatures, they do have ways of drying some of their gear overnight in tents. So that's sort of a question we'll get to down the road as we start talking more with soldiers and sort of engineering the product to their uses.
Okay. And as I understand the slide, the silver nanowires kind of grab on like a whole bunch of little Velcro threads or something? They just grab onto it?
They just strongly attach to the surface of the fibers, yes.
Okay. And when you talk about tweaking that you've done from Qui's work, what are some of the changes or advances that your group has made?
Yeah, so Dr. Qui's work was on cotton, which for the U.S. Army doesn't really serve that much of a purpose because most of our uniforms don't have 100% cotton. So we are translating this technology to a more suitable military fabric like polyester, polypropylene, NICO, which is 50% blend of nylon and 50% cotton. So we're translating his work into a more relevant work for the U.S. Army. Also, his work, he didn't do any laundering studies, and he didn't incorporate this hydrogel layer that we're trying to merge with the nanowires.
Okay, and would the hydrogel layer just stick on kind of like, because it's sort of a plastic?
Yeah, the first thing we'll try is just straight dip coating and see how adhered the particles are. But as Paola mentioned, you can pre-treat your fabric with plasma to enhance absorption of materials you deposit. And then if that's still not sufficient enough, we can consider covalent attachment of the particles to the fibers.
Covalent attachment, meaning
So it's
you make it, go ahead.
so it's like
You treat your fabric and you have reactive functional groups on your particles that can react with the fabric and link the materials, so they're
so
not
it
going to
won't
wash
come
off.
Yeah, they're not going to come off. And just to further answer your question, Dr. Cui was able to load about 0.6 milligrams of silver nanowires per centimeter square on their fabric. By tweaking a little bit of his methods, we have tripled that mass loading, which has resulted in higher heating capacity. So the work was inspired by his work. We're just like advancing it a little further to our needs.
Thank you.
Bela Buslik, ACS Communication. Is the silver nanowire layer in contact with the body?
Yes.
Okay, the question really was precipitated by silver nanoparticles have been used as an antiseptic cream of sorts. There was a question about washing off and so forth and contamination, so that might be one consideration.
Yes.
The other part is how durable are these fabrics? When you start laundering the thing, without the battery, of course, I can understand that it's a relatively, but when you've got a battery incorporated into the system, what do you do to launder the battery?
Yeah, so those are things that we have to take into consideration when we establish that collaboration with the professor in UC San Diego, because my understanding is that he has years of experience with electronic textiles and developing these batteries. So, but I don't know if he has studied any laundering or any like durability of these batteries. So those are questions that we're going to have to answer later on. But as I said at the beginning of the press conference, we are on the basic research stages of the project. And right now, we're just starting to move a little further into more like development. And
so obviously you're meaning to reuse the system.
Yes.
Not a single-use throwaway.
No. And well, right now, just by simply deep coating these swatches in silver nanowire ink, they perform as soon as you do them. They perform as well 10 months later. Maybe 10 to 12 months later, we're gonna start looking at oxidation of the nanowires, where they're gonna start affecting the performance. So right now we're trying to develop a protective coating that will prevent oxidation of these nanowires. But without this coating, this protective coating, the swatch lasts about 10 months, performing basically the same as day one.
Dr. Dollamore, American Chemical Society. It's said that an army lives and dies on its feet, and I'm wondering if there's any special adaptations that you wouldn't have to make for heating the feet or the socks or the boots with this technology.
Yeah, so right now, we're starting to think about adapting this technology to gloves and feet, socks, because, like for example, in the case of gloves, paratroopers are dropping when they're like 20,000 feet up in the sky, and they start losing feeling in their fingers within seconds. So as you can imagine, if you start losing feeling in your fingers, by the time they land, they basically have lost dexterity and the ability to operate weapons right away. So we're envisioning that this will go first as probably like to upgrade the handwear system of the cold weather uniform. And once that's done, then probably we'll move into socks and prevent like frostbite and things like that.
Great. Thank you very much, Drs. D'Angelo and Hirst. We appreciate your time today. The archived version of this session will soon be made available online at bit.ly/ACSlive_DC. Thank you very much, and join us for our next press conference at 11 a.m. today on the development of a new vaccine that could help fight the opioid epidemic. Thank you.